Hello, everybody. Welcome into another lesson. Happy New Year to everybody, and welcome to the first lesson of 2026. So, today we are going to talk about what are called piecewise functions. So, what are piecewise functions? Well, if we look at the notation here, we have f of x equals, then you have the big bracket here. It says f of x equals 5x minus 1 if x is less than negative 2. And then f of x equals x minus 9 if x is greater than or equal to negative 2. What that means is your function behaves like two or more. Sometimes you can have more than two functions in a piecewise function for certain sets of domain. It'll behave as two or more different types of functions. So if x is less than negative 2, my function's going to behave exactly like 5x minus 1. If the value of the domain, my value of x, is greater than or equal to negative 2, then the function behaves like x minus 9. So what we need to do here, plot a couple of points and graph the first part of this, because you can get some weird graphs for piecewise functions. But in order to graph, we need to plot points. So why don't we put in negative 3? No, let's not do that here. Yeah, let's put in negative 3. I don't think we go that far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alright, so if I put in f of negative 3, right? F of negative 3 is only defined for 5x minus 1, since you can only consider it if x is less than negative 2. Well, negative 3 is less than negative 2, so you would end up putting negative 3 into the 5x minus 1 piece of the function, which would give you negative 15 minus 1 would give you negative 16. So you would be at negative 3 somewhere all the way down here for your function. Now, disclaimer, we're still going to put in negative 2 into the 5x minus 1, but it's not going to be defined there. So if I put in f of negative 2 at 5x minus 1, I would end up getting negative 10 minus 1, which would give me negative 11. But when I get to negative 211, I'm going to draw a circle instead of a fully closed dot, because the value is not defined at negative 211. So 4, 5, 6, 7, 8, 9, 10, 11. So since my function is not actually defined there, I'm going to draw a dot, but I'm still going to connect the point between negative 3 and negative 2 for my x values. Now, what I really need to define here is f of negative 2 being at, since negative 2 is part of your domain for the function f of x equals x minus 9, if x is greater than or equal to negative 2, put in negative 2 for x minus 9, well, that would also give you negative 11. In this case, we can go ahead and color in the dot now, since it is defined at negative 211, since negative 2 is defined for x minus 9 if x is greater than or equal to negative 2. Now let's plot, why don't we do f of 0? F of 0 would give us 0 minus 9, which would give us negative 9. So at 0, we're going to be at negative 9. Let's go ahead and start drawing the line there. And then why don't we do f of 9? F of 9 would give you 9 minus 9, which would be 0. So you'd also get the point 9, 0. Then we'll just go through it. So that's your piecewise function. Where x is greater than or equal to -2, it's going to behave like x minus 9. It'll behave like f of x equals x minus 9. If x is less than -2, it's going to behave like the line 5x minus 1. And together, when you combine them, you get this weird curvature in the line. You get this weird kink in the line, so to say, because you've really fused two lines together at that point. And I got more examples of this. All right. Ooh, that's not right. There we go. So what if I had this piecewise function? Alright, so I have a piecewise function here where f of x would be equal to -x if the value of x is greater than 2. So for all values where x is greater than 2, my function is going to behave like f of x equals -x. If I have values less than or equal to 2, my function is going to behave like f of x equals x minus 4. So let's start with the less than or equal to 2. Why don't we do 2 itself, right? If I want to put in f of 2, well, f of 2 is only defined if x is less than or equal to 2. Well, that'd be equal to 2 minus 4, which would be -2. So 2, -2 would actually be a point on the graph then. And then, why don't we put in f of 0? Since 0 is less than or equal to 2, we'll put that in for x minus 4. So 0 minus 4 equals -4. So 0, -4 would be a point. And I could just connect the dots and draw my line. Okay. Now, let's deal with if x is just greater than 2. Well, let's put in 2 itself into -x, even though it wouldn't be defined there, you would still get -2. And you can have disconnected graphs, by the way, of piecewise functions. You can sometimes have that. In fact, we'll do an exercise like that in a minute where it's disconnected. But anyway, in this case, if you put in 2 for -x, you would also get -2. It checks out there. But what about 3? What if we were to evaluate f of 3? You can only evaluate f of 3 for -x if x is greater than 2. So you would get -3. So at 3, you would be at -3. Heck, well, for good measure, let's do f of 4. Well, x is greater than 2, 4 is greater than 2, so negative of that would be -4. So you get the point 4, -4. So just go ahead and connect your dots, and you have the other side of the piecewise function. So when x is greater than 2, it behaves like f of x equals negative x. When x is less than or equal to 2, f of x behaves like x minus 4. And the two fused together produce this graph. Whoops, I better erase the graph itself because we're going to get something different in the next one. Alright, so what if we had f of x piecewise function is equal to x plus 6 when x is less than or equal to negative 3, and then it's also equal to negative 2/3 x minus 3 when x is greater than negative 3. So we have another piecewise function here where f of x equals x plus 6 when x is less than or equal to negative 3. Excuse me. And then we have f of x equals negative 2/3 x minus 3 when x is greater than negative 3. So let's start with the portion where x is less than or equal to negative 3. Let's put in f of negative 3 itself, right? F of negative 3 can technically only be evaluated at x plus 6 since that's the function for the part of the domain where x is less than or equal to negative 3. So you would get negative 3 plus 6, which would also give you negative 3. So you have the point negative 3, well, actually that'd be positive 3, my bad. I don't know what I'm thinking. You would get negative 3, positive 3. Alright, and let's see. Let's do negative 6. F of negative 6, which is also less than negative 3. So put that in for x plus 6. Well, you would get a value of 0. So negative 6, 0 would actually be a point. Now just connect your dots from there. Draw your line going further left through the 2 points. Okay. Now here's where it gets fun. Let's also, we have x is just greater than negative 3. However, let's put in negative 3 into the second bottom function for the sake of finding where the discontinuity is. So f of negative 3 would equal negative 2/3 times negative 3 minus 3. Well, that would end up giving you 2 minus 3, which would give you negative 1. Well, if you put in negative 3 into the second bottom function, you get negative 1. Now, since negative 3 in the domain is not defined for the bottom function, you're going to put a hole at negative 3, negative 1. The reason being is because f of negative 3 is not defined for negative 2/3 x minus 3. Now let's find another point here. Why don't we do f of 0? Well, 0 is definitely greater than negative 3. Well, that would just give you negative 3. So you'd have the point 0, negative 3, which is defined. Now you'll connect the discontinuity to the point 0, negative 3, and you'll continue drawing your line through 0, negative 3 to the right. And when you have piecewise functions, you can get graphs such as this where there's a disconnect in the two lines. Because if you have the point negative 3, negative 1, that's not defined for negative 2/3 x minus 3. but negative 3, positive 3 is defined for x plus 6. So that's why we have the discontinuity with the hole in it at negative 3, negative 1. Alright, so that's an example that you can't always trust that the two functions will come together at some point. They don't always do that. Alright. Let's see here. I'd like to do a couple more. F of x equals, this is another piecewise function where you have 3x minus 14 when x is less than or equal to 4. And then you have negative 2x plus 6 when x is greater than 4. So here's another piecewise function. F of x equals 3x minus 14 when the value of x is less than or equal to 4. It'll behave like that function. And then you have f of x equals negative 2x plus 6 when x is greater than 4. It'll behave like that function. So let's start with the less than or equal to 4 part. Of course, let's put in f of 4 itself. F of 4 is defined for the function 3x minus 14. So you put in 4 for x, you would end up getting 12 minus 14, which would equal negative 2. Alright, so at 4, you would be at negative 2. Now, what if we put in 3? Let's put in f of 3. 3 times 3 is 9. You'd have 9 minus 14, which would end up giving you negative 5. So at 3, you're down to negative 5. And then, why don't we do f, well, let's not do f of 0. That's going to be awful. In fact, we could just draw the function here. Just connect your two dots and draw the line for x getting smaller and smaller. Alright, now we have the part where x is greater than 4. Just greater than 4, but we still need to put in f of 4 for the bottom function so we know where discontinuity might occur. So if we put in f of 4 for negative 2x plus 6, you would end up getting negative 8 plus 6. Well, that still gives you negative 2. So we don't need to put a hole because it's defined in the first function. It tends to overlap the second function. So we're good there, but what about f of 5? F of 5, well, negative 2 times 5 is what? Negative 10 plus 6, which is negative 4. So at 5, you would be back down to negative 4. And then you could just connect your dots and go further down. And there would be the graph of this piecewise function. When you connect the two lines together, you get the graph of that piecewise function. Got one more piecewise function, then we're going to do what's called the greatest integer function, which won't be that long. Alright, so let's see. F of x equals x minus 8 when x is less than 9. We got 1/3 x minus 2 when x is greater than or equal to 9. Okay. So we have another piecewise function. This time you have x minus 8. When x is less than 9, the function will behave like f of x equals x minus 8. When x is greater than or equal to 9, the function will behave like f of x equals 1/3 x minus 2. Let's start with the less than 9. So we need to put in 9 for the x minus 8, even though it's not defined there. We want to find where the discontinuity is. So f of 9 for the top one, that of course would equal 9 minus 8, which would give you 1. 2, 3, 4, 5, 6, 7, 8, 9. Which would put you at the point 9, 1, and you would actually draw a hole there instead of a solid dot because it's not defined for x minus 8. Then of course let's put in f of 8. F of 8 itself would be equal to, of course, 8 minus 8, which would be 0. F of 8 is defined in x minus 8 since the value of the domain is less than 9. So 8, 0 would be defined. And of course, why don't we put in f of 0? F of 0, of course, 0 minus 8, that would give you negative 8. So 1, 2, 3, 4, 5, 6, 7, 8. So draw your function of x minus 8 starting at the point 9, 1 where the discontinuity is and going further left since x is less than 9. Now let's figure out x is greater than or equal to 9. We can for sure take f of 9 in the bottom function since the value of x can be greater than or equal to 9. So f of 9 would equal, what's a third of 9? That's 3 minus 2, which is also 1. Well, all of a sudden 9, 1 now is defined. We can color in that dot. What about f of 12? If I put in f of 12, a third of 12 is 4 minus 2. Well, that would give me 2. So I would be at the point 12, 2 up here. So my line would veer off that way. I would get kind of a funny bowing of the line, and that's what the graph of my piecewise function would look like. So those are piecewise functions. Let's talk about greatest integer functions now. Those are really kind of cool themselves. Alright, let's say you have something like this. This is called the greatest integer function. F of x equals the greatest integer of x. So what is that exactly? What is the greatest integer of x? This is going to produce what looks like a step function. Now, for a step function, here's what it means. The greatest integer. Let's say you put in 0, right? Well, f of x is still equal 0. So you'll plot the point 0, 0. But every number up until 1, up until x equals 1, will round to y equals 0. And then when you get to 1, it won't be defined at first because you're still rounding down to where your y equals 0. Now if you go to put in 1 for your x, you're going to start with a y value of 1, and go all the way till you reach an x value of 2 and put a solid dot there. And then go to f of 2, you'll put a solid dot at 2, 2. Go over to 3, 2, you put an open circle at 3, 2 since it's not defined there. Then go to 3, 3, you would put a solid dot there. And then go to 4, 3, put a open circle since the function wouldn't be defined at 4, 3. But at 4, 4 it is. Put a dot at 4, 4 and then go till you reach 5. Put an open dot there. Of course, we could go from -1 to 0. We could do the same thing here. -2 to -1. -3 to -2. So you see the step pattern. I'm sure by now you see the step pattern. That's what the greatest integer function does. You start with your x value, which would also be your y value. So at f of 0, you would initially get 0, but every number in between 0 and 1 is going to round down. It rounds down to y being 0. And then, of course, you're going to put a dot at 1, 0 since 1 itself doesn't round down to 0. But then when you put in f of 1, you'll get 1, 1, and you'll go all the way till you reach f of 2, or where x equals 2, you'll put an open circle there since it's not defined at 2, 1. But every point between 1 and 2 would round down to y equaling 1. Then once you put in f of 2, you'll put a dot at 2, 2, since, of course, at 2 the function would round to 2. So every point between 2 and 3 would round down to y value being 2. Then once you reach 3, 2, you put an open circle there since the function wouldn't be defined at 3, 2. And you keep doing that for every integer. That's the pattern for every integer. The greatest integer function can also be called the floor function. It's also known as the floor function. So this here is your greatest integer function. And then this right here is the floor function. It goes in a step pattern where every number you put in between the number you just put in and the very next integer up to the next integer, it rounds down to the nearest number for your y value. And then, then you repeat the process for the subsequent integers. So that's an example of the floor function. Now, there is a ceiling function, which I will also demonstrate. Have to destroy part of this graph here, but that's okay. What if... So you see the bracket for the floor function. It looks like it looks like an L and then a backwards L. Well, there is a ceiling function too. Another example. Alright, so here is the ceiling function. So what does the ceiling function do? The ceiling function is different. If I put in f of 0, every number between 0 and 1 will automatically round up. The ceiling rounds it up. So you think of the floor, you stay down. The ceiling, you go up. You round up. So every number between 0 and 1 on the x-axis will automatically round up to 1 for your y value. But at f of 0, I'm going to put an open dot at 0, 1 because 0 obviously itself doesn't round up to 1. It's undefined there. But I'll put a dot at 0, 1 since it every number between 0 and 1 rounds up to 1. And then when I get to, of course, 1, 2, when I go above it in the step pattern, well, 1 itself doesn't round up to 2, but I'll put a dot at 1, 2 to denote it's undefined there. But every number between 1 and 2 will automatically round to 2. So I'll put a dot at 2, 2. So I'll have an open circle at 1, 2. And then a dot at 2, 2. So that denotes that every number in between 1 and 2 is rounding up to 2. And then when I get to 2, 3, go right above 2, 2, I'll put a dot there because 2 itself doesn't round to 3, but every number between 2 and 3 will round to 3. So I'll put a dot at 3, 3, and then I'll connect those two. Then if I go to 3, 4, I'll put a dot, I'll put an open circle at 3, 4 since 3 doesn't round to 4, but every point between 3 and 4 round up to 4. So you're probably starting to see the stair-step pattern. Now, of course, if I want to go negative, negative 1 itself wouldn't round to 0, so I'd put an open circle there, but every number between negative 1 and 0 would round to 0. Then negative 2. Well, negative 2 itself wouldn't round to negative 1, but every number between negative 2 and negative 1 would round to negative 1. Then negative 3, well, negative 3 itself doesn't round to negative 2, but every number between negative 3 and negative 2 would round to negative 2. So I'm sure you're starting to see that stair-step pattern. The differences between the last one and this one is you're rounding everything up as opposed to rounding down like you did with the floor function or the greatest integer function. And we're really not going to do much with these. The ceiling and floor, this might really be it for those. I just wanted to show those to you and show you can get some neat graphs. And these are functions. You know why they're functions? Because if you take the vertical line test, even between the undefined point and the defined point, you have a vertical line passing through a hole. So it actually does not fail the vertical line test. The vertical line test would only fail if it was a continuous curve and it went through two solid points. So that's how these can still maintain being functions. But that's it for this lesson. Next lesson we are going to talk about absolute value functions and their graphs. And then we'll even get into a bit of shifting and reflecting and stretching of graphs and what different equations mean for that. So I do hope everyone has a great day. Take care.